Imagine looking up at the night sky, filled with countless stars, and realizing that some of those twinkling lights are not stars at all, but human-made satellites silently orbiting our planet. The story of satellites begins in the mid-20th century at the height of the Cold War. On October 4, 1957, the Soviet Union launched Sputnik 1, the world's first artificial satellite. This metal sphere, just 58 centimeters in diameter and weighing 83.6 kilograms, marked humanity's first step into space. Sputnik 1 was a simple transmitter that emitted beeping radio signals, but it sparked the imagination of scientists and the public alike. It demonstrated that we could send objects into orbit around Earth, opening up a new frontier for exploration and communication. Sputnik's success was a wake-up call to the world, showcasing the Soviet Union's technological prowess and prompting the United States to ramp up its own space efforts, leading to the creation of NASA in 1958. Following Sputnik, a series of pioneering satellites emerged. The United States responded with Explorer 1, launched on January 31, 1958. Explorer 1 carried scientific instruments, including a cosmic ray detector that discovered the Van Allen radiation belts, zones of charged particles trapped by Earth's magnetic field. This marked the beginning of using satellites for scientific discovery. As the space race heated up, satellites became more sophisticated. By the 1960s, satellites like Telstar and Syncom were facilitating the first live transatlantic television broadcasts, shrinking the world and revolutionizing global communications. These early satellites laid the groundwork for the complex and diverse satellite networks we rely on today, spanning communication, weather forecasting, navigation, and scientific research. Building a satellite is a complex process involving cutting-edge technology and meticulous engineering. Satellites are constructed in clean rooms to avoid contamination, as even a speck of dust can compromise their functionality in space. These clean rooms maintain strict environmental controls, ensuring that the delicate components are assembled in pristine conditions. The construction of a satellite involves integrating various subsystems, each critical to its operation. The power subsystem typically includes solar panels that convert sunlight into electricity and rechargeable batteries to store energy for periods when the satellite is in Earth's shadow. The communication subsystem consists of antennas and transponders, which receive, amplify, and retransmit signals to and from Earth. Control systems are essential for maintaining the satellite's orientation and position in space. These systems include gyroscopes, reaction wheels, and thrusters that make precise adjustments to keep the satellite stable and on course. Payloads vary depending on the satellite's mission, from cameras and sensors for Earth observation to transponders for communication satellites. Once built, satellites are transported to the launch site, often a spaceport like Kennedy Space Center in Florida or Baikonur Cosmodrome in Kazakhstan. There, they are integrated with a rocket, which serves as their ride to space. The cost of building and launching a satellite can range from tens of millions to billions of dollars, depending on its size, complexity, and mission. Launching a satellite is a high-stakes endeavor, with extensive planning, testing, and safety measures in place to ensure success. The launch itself is a carefully orchestrated sequence. The rocket ignites, producing millions of pounds of thrust to escape Earth's gravity. As it ascends, different stages of the rocket burn out and detach, eventually placing the satellite into its designated orbit, which could be low Earth orbit, LEO, medium Earth orbit, MEO, or geostationary orbit, GEO. Each orbit serves different purposes, with LEO often used for imaging and research satellites, MEO for navigation satellites, and GEO for communication satellites that remain fixed relative to a point on Earth. Once in orbit, satellites are controlled from ground stations on Earth. These stations send commands and receive data, ensuring the satellite operates correctly. Ground control teams monitor the satellite's health, performance, and position, making adjustments as needed. Satellites use onboard thrusters for minor adjustments to their orbit, maintaining their position and orientation to fulfill their mission objectives. Satellites play a crucial role in modern communication. They receive signals from Earth, amplify them, and retransmit them to different locations. For instance, when you make a phone call or stream a video, the data might travel from your device to a ground station, then up to a satellite, and back down to another ground station before reaching its destination. This process happens almost instantaneously, allowing for seamless global communication. Satellites are equipped with transponders that convert signals to different frequencies, preventing interference and ensuring clear communication. They also carry solar panels to generate power, batteries for energy storage, and thermal control systems to handle the harsh conditions of space. The onboard computers and software manage the satellite's functions, processing commands from ground control and executing tasks autonomously. In addition to communication, satellites serve various purposes. Weather satellites, such as those in the Geostationary Operational Environmental Satellite (GOES) series, monitor weather patterns, helping meteorologists predict storms and track climate change. Earth observation satellites, like those in the Landsat program, capture detailed images of our planet, providing valuable data for environmental monitoring, agriculture, and urban planning. Navigation satellites, part of global systems like GPS, GLONASS, and Galileo, provide precise location and timing information, essential for navigation in aviation, maritime, and everyday applications like driving and geocaching. Scientific satellites such as the Hubble Space Telescope explore the cosmos, revealing the mysteries of distant galaxies, black holes, and the origins of the universe. Satellites have a limited lifespan, typically ranging from 5 to 15 years, depending on their mission and design. Factors affecting their lifespan include the degradation of solar panels, battery life, and wear and tear from the harsh space environment, including radiation and micrometeoroids. When satellites reach the end of their operational life, they face different fates. Some are moved to a graveyard orbit, a safe distance from active satellites, while others are deorbited to burn up in Earth's atmosphere. For communication satellites in geostationary orbit, the graveyard orbit is a region several hundred kilometers above the operational geostationary belt. Moving a satellite to this orbit requires using the remaining onboard fuel to raise its altitude, ensuring it does not interfere with active satellites. Low Earth orbit satellites, on the other hand, are often deorbited to re-enter the atmosphere, where they burn up upon re-entry, minimizing the risk of space debris. If a satellite malfunctions or is damaged, repair is rarely an option due to the high cost and complexity. Historically, only a few repair missions have been conducted, such as the Space Shuttle missions, to service the Hubble Space Telescope. These missions involved astronauts performing spacewalks to replace faulty components and upgrade instruments, extending the telescope's life and capabilities. However, there are ongoing developments in space robotics and servicing missions aimed at extending satellite lifespans and reducing space debris. Companies and space agencies are developing robotic spacecraft capable of refueling, repairing, or even repositioning satellites. These servicing missions could revolutionize satellite operations, making space more sustainable and cost-effective. The future of satellites is bright and evolving rapidly. New technologies, such as miniaturized satellites called CubeSats, are making space more accessible than ever. CubeSats are small, standardized units that can be combined to form larger satellites. They are cost-effective to build and launch, allowing universities, startups, and even high schools to participate in space missions. These tiny satellites are used for a variety of purposes, from scientific research to technology demonstration and Earth observation. Large constellations of small satellites are being launched to provide global internet coverage, transforming how we connect and communicate. Companies like SpaceX, with its Starlink project, and OneWeb, are deploying thousands of satellites to create networks that can deliver high-speed internet to even the most remote areas on Earth. These constellations promise to bridge the digital divide, bringing connectivity to underserved regions and revolutionizing industries from agriculture to disaster response. Satellites continue to revolutionize our understanding of Earth and space, from monitoring climate change to exploring distant planets. Earth observation satellites provide critical data for tracking environmental changes, managing natural resources, and responding to natural disasters. Scientific satellites, such as the James Webb Space Telescope, set to launch in the near future, will probe deeper into space than ever before, seeking answers to fundamental questions about the universe. As we look up at the night sky, we can marvel at the ingenuity and perseverance that have brought these silent sentinels into orbit, forever changing our world. The ongoing advancements in satellite technology and space exploration promise a future where satellites play an even more integral role in our daily lives and our quest for knowledge. In conclusion, satellites are a testament to human ingenuity and ambition. From their humble beginnings with Sputnik 1 to the sophisticated networks that power our daily lives, they have become an indispensable part of modern society. As we continue to innovate and explore, the role of satellites will only grow, paving the way for new discoveries and advancements. The sky is no longer the limit, but just the beginning.